All right, well, welcome to the first video of online mathematical modeling, MTH 380. We are going to be starting a new unit, and in this unit, we're going to be focusing on modeling change. So we're going to be looking at a type of mathematical model called a discrete dynamical system, or sometimes it's called a difference equation. And we're going to see how we can use these sorts of models to describe change, how we can construct models by using our intuition about the relationships between some of the components of a system, and then we'll also look at some of the mathematical methods for analyzing these sorts of models in order to better understand what sort of predictions they make. And this is a very timely topic. One of the types of dynamical systems models we're going to look at would be epidemic models. And so maybe after getting through this subject, you'll have a little bit of a better understanding of what's going on in regards to this coronavirus outbreak that has prompted our switch to an online format. All right, well, let's get started. So, first of all, there are lots of different types of models that one might study. And up to this point, we focused primarily on static models. So we looked at models where we were trying to find a relationship between two variables. And every once in a while, we used time as one of the variables, but more often than not, it was just a relationship between two variables that were constant. We also looked at optimization models, and in optimization models, we're trying to find the best solution, but more often than not, that has nothing to do with time. In a dynamic model, all of the variables that we're describing are changing, or at least many of them are changing over time, and we want to be able to track those changes and ultimately make some sort of forecasts about what those changes are going to look like in the future. Now, there are two different types of models that can be used to describe dynamical systems that are changing. You can use continuous models where time is a continuous variable, and in that case you will need what's called a differential equation to describe the system. Now, our math department does offer a course in differential equations, and so rather than rehashing all the material that is offered there, I'm going to primarily focus on the other type, which is a discrete model, where we're going to think of time as a discrete variable. It's going to have some sort of steps in time that are not infinitely small, and we'll try to figure out how do we predict the state of the system at one time given the state in the previous time. All right. The last distinction we want to make here is between models that are deterministic and models that are stochastic. So in a deterministic model, once you know the initial state of the system and you know the rules that govern the changes in the system, you can determine exactly what's going to happen in the future. In a stochastic model, we incorporate some sort of randomness. So maybe the ways that the amount that different quantities are going to change is going to be a random variable. Maybe some of the parameters of the model will be random. There's various ways to incorporate randomness, but if we have a stochastic model, if we've incorporated some randomness, then every outcome of our model is going to be slightly different. And so we're going to want to make different sorts of claims about the model. More specifically, we're going to be interested in making claims that are probabilistic in nature. What is the probability that the outcome looks like X or Y? Okay? All right, so that's where we're headed. Let's start by thinking about discrete dynamical systems, and we're going to look at deterministic models first, and then we'll get to stochastic models in our next unit. All right, so the fundamental principle we're going to be looking at when we're creating these models is that the future value of the state of the system is equal to the present value plus some change. Seems pretty intuitive. Essentially, we're just going to have to describe the change, and that will allow us to determine how to make predictions into the future. And mathematically, we can define some variables. We've got a variable t, which is going to represent time, and we're going to have some sort of time step, delta t. And for the most part, we're going to focus on the case where that time step is constant, so we're not going to change the step size. But you can think of that as moving forward one unit of time. And that unit could be a minute, could be an hour, could be a day. Depending on the context, it may make sense to use a variety of different values, but we're going to use, again, a fixed time step. So what this means is that we can find the state of the system, which I'm calling a of t plus delta t. So that's the new state based on the current state. Plus some change term. And the change, which I'm denoting delta A, could in principle depend on a bunch of things. It could depend on the value of time. It could depend on the value of A. It could depend on how much of whatever the variable we're trying to quantify we have. And it could depend on a variety of different parameters. And so most of our modeling effort is going to go into describing this change term. All right, so let me introduce a little bit of notation. I mentioned delta t a moment ago. We're also going to think about taking snapshots of the system where we're going to use a subscript n to denote which time we're looking at. And so we'll define Tn, little subscript n is going to denote the time step, and that's just going to be how many delta t's do we have. So T1 would be delta t, T2 would be 2 delta t, and so on. All right, and for shorthand, since it gets annoying to have to write parentheses Tn every time we want to reference the value of a at a particular time, we'll use the shorthand a subscript n to denote the state of the system at time n. And similarly, we'll define delta a with a subscript to allow the change to potentially change over time. So delta a n plus 1 is going to be the difference between the new state and the old state, or a evaluated at time Tn plus delta t minus a evaluated at time Tn. Okay, so now that we've got the notation in place, let's think about what we would need to do to describe a discrete dynamical system. Well, there's really two pieces of information that we need. We need to know, first of all, the initial state. Notice that this equation at the bottom, which summarizes what we talked about a minute ago, the next state is dependent on the previous one. Well, if we're going to use that, we have to be able to start somewhere. And so we're going to need to know what was the value of a initially before we can start finding a1, a2, a3, and so on. So the initial state is required. And then the second thing is we need to describe the change. And typically this change is going to be a function of the time, the function of the state, and then it will often be proportional to delta t, meaning that the longer you wait, the larger the change is going to be. All right, so as an example, let's suppose that we're given an initial state of 1. The value of a at step 0 is 1. And we've got a function here to describe the change. So the change in a is going to be delta t times negative 1/2 times the state at time n. Let's see if we can use that model to compute some predictions. All right, so if we have, I'm going to use the side here. We have a0 equals 1. Well, the formula says that a1 should be equal to a0 plus delta a1, which that is going to be, if we plug in our formula for the change, that would be, well, a0 is 1 plus delta t, which we're using delta t equals 1, times negative 1/2, times an, which was the last value, which again 1, and so our new value of a would be 1 minus 1/2, so it would just be 1/2. And we could apply that to the next time step. So a2 is going to be a1 plus delta t times negative 1/2 times a1. And plugging that in, we'll have 1/2 plus 1 times negative 1/2 times 1. And so that's going to give us, it looks like, a1 was 1/2, and so that'd be 1/2 minus 1/4. So now we're going to be at 1/4, and we could do that one more time. a3 is going to be a2 plus delta t times negative 1/2 times a2, which is going to be 1/4 plus 1 times negative 1/2 times 1/4, and so now we're going to be at 1/8. Okay, so that's how we can actually use the formula once we filled in the initial value and the change. Essentially, you have to go one step at a time. Given the initial state, you find a1. Given a1, you find a2. And given a2, you can find a3. And you'll notice that if we wanted to find a100, this would be a very tedious process. And so one of the techniques that we're going to use down the road is use a computer to do all of this rather tedious work for us. All right, I will stop here for the first video, and we'll continue our discussion in the next.